Welcome back to AI.Code.Cast. Today, we're doing a deep dive into a classic coding puzzle.
Right.
It's all about finding peaks. Well, peak elements in an array, that is.
Okay.
Imagine you're given this list of numbers,
Yeah.
and you need to find a value that's bigger than its neighbors on both sides.
Right.
Sounds simple enough, right?
Yeah, it can be.
But the real challenge, I think, is to find these peaks efficiently, especially when you're dealing with massive data sets.
Yeah, that's right. Think about trying to find the highest peak, like the highest point in a mountain range.
Yeah.
You wouldn't want to hike up every single peak, to figure out which one is the tallest.
Right.
You'd want to have a smarter strategy.
Yeah.
So before we get into those clever strategies, let's just break down what exactly we mean by a peak element in an array.
Yeah. Good idea.
For example, say we have an array like this: 1, 3, 2, 5, 4.
Okay.
Which elements would be considered peaks?
Well, in that example, the 3 and the 5 would be peaks because they are larger than both of their neighbors.
Right. Exactly. It's like they're standing taller than the numbers on either side.
Right.
But here's a question. What if we have an array like this? 1, 2, 2, 1. Are there any peaks there?
That's a good question. In that case, I don't think any of the elements would be a peak because none of them are strictly greater than both of their neighbors.
Good point. And to clarify, we usually, in most variations of this problem, only need to find one peak.
Okay.
Not necessarily all of them.
So even if we had multiple peaks in an array, our goal would just be to find one of those peaks.
Exactly. So even if there's multiple, our goal is just to return the index of any single peak.
Right.
So I know what you're thinking. Couldn't we just go through the array and compare each element to its neighbors?
Yeah.
And just stop once we find one that fits that definition?
Yeah, that's definitely a valid approach.
Yeah.
And probably the first one that comes to mind.
Exactly. We call that the brute force method. It's kind of straightforward, doesn't really require any fancy algorithms.
Right. Yeah. So it seems simple enough. So what's the catch?
The catch is efficiency.
Okay.
Especially when you start to deal with really large arrays. Imagine an array with millions or billions of elements. Going through each one individually would take a considerable amount of time.
Yeah, so while the brute force method works, it's not the most elegant or scalable solution.
Exactly. That's where things get a little bit more exciting. In computer science, we're always trying to find more efficient solutions.
Okay.
So how can we find a peak element without having to look at every single element in the array?
Yeah.
What do you think?
Well, if we're looking to speed up the search, maybe we could try dividing the problem in half repeatedly. Kind of like how we search for a word in a dictionary.
Interesting thought. You're onto something there.
Okay.
That sounds a lot like a binary search, which is typically used for finding specific values in sorted arrays.
Right.
But how would we apply that to an array that might not be fully sorted?
Yeah, that's what I was thinking.
That's the clever part. That's the beauty of this problem.
Okay.
The beauty of this problem is that we can adapt binary search to work even if it's not fully sorted.
Yeah.
The key is really understanding the fundamental property of a peak element and how that relates to the array's structure.
Okay, I'm intrigued.
Yeah.
How do we, bend binary search to our will?
Let's unpack that in the next part of our deep dive.
Okay. All right, so we left off talking about using binary search to find a peak element.
Right.
Even if our array isn't sorted in a normal way, I'm still a little fuzzy on how that would work.
Yeah, it's a clever trick for sure.
Okay.
Remember how binary search usually needs a sorted array to decide which half to search next?
Right.
Well, with peak finding, we can actually use the slope of the array to kind of guide our search.
Slope. What do you mean?
Okay, so imagine our array is like a mountain range with each element the height of a peak, right?
Okay.
If we're standing on a particular element and it's smaller than its neighbor to the right, then we know we're on an uphill slope.
Right. So the peak must be further to the right, somewhere along that uphill path.
Exactly. That's the key insight. So in that case, we can safely discard the entire left half of the array and focus our search on the right.
Makes sense. But what if the middle element is larger than its right neighbor?
Then we could be at the peak itself, or we could be on a downward slope. Either way, the actual peak can't be to the right.
So we discard the right half and focus on the left.
Yes.
Including that middle element.
You got it. So with each comparison, we're basically narrowing down our search space. Kind of zeroing in on a target. And we keep repeating this, comparing the middle element to its right neighbor and having the search space until
we find our peak.
Exactly. Until we have a single element left, which must be the peak.
Okay, that makes sense. So I know we've been talking about this conceptually,
Right.
but how would we translate this logic into, like, actual code?
Well, let's try to sketch out a basic algorithm. We can use pseudocode.
Okay.
That way we can see the structure without getting bogged down with the specific syntax.
Right, yeah. I'm a big fan of pseudocode. It's like a blueprint for our algorithm.
Exactly. So first, we need to define a function.
Okay.
We can call it findPeak,
Okay.
which would take an array as input. And inside this function, we'd initialize 2 pointers. We can call them left and right,
You're right.
which initially point to the beginning and end of the array, respectively.
So left would start at index 0.
Yes.
And right would start at the last element, or the index of the last element.
Right, marking our search boundaries.
Right.
Then we can use a while loop to keep running this binary search logic as long as left is less than or equal to right.
Which makes sense because the loop will stop when our search space collapses down to just one element.
Right. And inside the loop, we'd calculate the middle index.
Okay.
We can call it mid by averaging left and right.
Okay.
And this is like the element we'll use to compare with its right neighbor.
Got it.
And then, here's the decision-making part.
Right.
We check if the element at mid is greater than the element at mid plus 1.
Okay.
If it is, meaning it's on a descending slope,
Uh-huh.
we'd update right to be mid, so we're discarding the right half of the array.
Okay.
And if the element at mid is less than or equal to the element at mid plus 1,
Meaning we're on an ascending slope or at the peak?
yeah, then we'd update left to be mid plus 1.
Right. Okay. So we keep looping through this logic, narrowing down our search space until...
Yeah, left and right meet.
Uh-huh.
And at that point, the element at index left or right, because they're the same,
Yeah.
that would be our peak.
I see. So it's like strategically folding the array in half over and over until we find the highest point.
Exactly. And, the beauty of this binary search approach is it's incredibly efficient.
Yeah.
Especially for very large arrays.
How much faster are we talking compared to the brute force method?
Well, the brute force method has what we call a linear time complexity, meaning the time it takes grows proportionally with the size of the array.
Mm-hmm.
But binary search has something called a logarithmic time complexity.
Logarithmic. That sounds a lot better.
It is. Imagine searching through a phone book with 1,000,000 entries.
Okay.
With a linear search, you might have to look through every single entry, in the worst case scenario.
Yeah.
But with binary search, you could find your target in something like 20 comparisons.
Wow, 20 versus 1,000,000. That's a pretty big difference.
It is. It's like having a map that lets you teleport halfway up the mountain each time,
Right.
instead of having to hike up every single step of the way.
I love that analogy. So are there any potential pitfalls or edge cases we should be aware of with this binary search approach?
That's a great question. There's a few things we need to keep in mind, like what if our array is empty?
Right.
Or what if there are multiple peaks?
Yeah, those are good points.
Yeah.
I guess an empty array is easy enough to handle.
Yeah.
We could just check at the beginning of our function to see if the array has any elements at all before continuing.
Exactly. And as for multiple peaks, our goal is just to find any peak.
Right.
It doesn't have to be the highest one.
Right, so it doesn't matter if there's multiple peaks.
Exactly. So our binary search will still correctly find one of them.
Okay, that's reassuring.
Eh.
So are there any other ways to solve this peak finding problem?
You're always thinking outside the box.
Uh-huh.
And the answer is yes. There are some other interesting approaches we could explore.
Oh.
One of them involves a technique called a linear scan, which, while seemingly simpler, has its own advantages in some situations.
Oh, interesting. So is that similar to the brute force approach we talked about?
It is similar.
Just going through the array element by element?
It's similar, but with a few, clever tweaks.
Okay.
In a linear scan for peak finding, we leverage the fact that adjacent elements in our array are guaranteed to be different.
Right. Okay.
So that allows us to make some optimizations.
How so?
For example, let's say we're going through the array.
Okay.
And we find an element that's bigger than its right neighbor.
Yeah.
We know for sure that that's a peak. We don't even need to check its left neighbor.
Oh. Because if it's already bigger than its right neighbor and adjacent elements can't be equal,
right,
it must be bigger than its left neighbor as well.
Exactly. So in a linear scan, we can potentially find a peak much faster than if we were comparing each element to both of its neighbors every time.
That's a neat trick. So even though it's still like a linear approach in essence,
Yeah.
we're taking advantage of the problem's constraints to make it more efficient.
Precisely. And in some cases, especially if the array is like relatively small,
Okay.
this linear scan approach might even be faster than binary search
Oh, interesting.
because it has less overhead.
So it seems like there's often more than one way to solve a problem.
Yeah.
And the best approach might depend on the specific circumstances.
Absolutely. That's the beauty of algorithm design. It's not just about finding a solution, it's about finding the best solution for the given context.
I'm really enjoying this conversation.
Me too.
We've covered binary search and linear scans. Are there any other peak finding techniques that you think are worth talking about?
There's one more that's like quite elegant, though it might be a bit more advanced.
Okay.
It involves using something called recursion to break down the problem into smaller subproblems.
Recursion. That sounds interesting.
Yeah, so in the context of peak finding,
Okay.
we can use recursion to basically divide the array into smaller and smaller chunks
Okay.
until we find a peak.
I see. That sounds similar to how we use binary search to divide up the search space.
Exactly. But instead of explicitly using pointers like left and right,
Okay.
we can actually use the function's call stack
Okay.
to keep track of those boundaries.
So we're using function calls to narrow down the search.
Precisely. And like binary search, this recursive approach has a logarithmic time complexity.
Which is great for large arrays.
Right.
Wow. We've covered a lot of ground today. Binary search, linear scans, and recursion.
Yeah, it's amazing how many ways there are to approach this seemingly simple problem.
Right.
It really goes to show that algorithm design is like a very creative and multifaceted field.
I'm totally hooked.
Me too.
But I think we've talked a lot about this already. Maybe it's a good place to pause for now.
I agree.
But before we sign off, I want to leave our listeners with a bit of a challenge.
Oh, a challenge. I love a good challenge.
So we've talked about several different techniques for finding a peak element in a static array.
Right.
But what if our array is dynamic? What if we can add or remove elements from the array as we go?
That's a good one.
Yeah, our existing algorithms might not be efficient if the array is constantly changing.
Exactly. So to all our listeners out there,
Yeah.
if you're feeling ambitious, think about how you would adapt these techniques to work efficiently on a dynamic array.
That's a great challenge. It'll make you think about how to apply what we've learned in a more real-world scenario.
Yeah, I agree. And who knows, maybe we'll even feature some of your creative solutions in a future episode.
That would be awesome. So to all our listeners, keep those algorithms humming, and we'll catch you next time on AI.Code.Cast. Welcome back to AI.Code.Cast. So before we got a little sidetracked with those dynamic arrays, we were in the thick of it, talking about peak finding and all the cool ways to solve this challenge.
Yeah, we went all the way from that brute force method to that super elegant binary search, even touched on linear scans and recursion a bit.
Yeah, it's amazing how many different paths can lead us to the top of the mountain, right?
Exactly. Each approach has its own strengths, its own weaknesses. And the being a choice, I think, depends on, the specific array, how it's structured, and the limits we have to work with.
But you threw us for a loop with that dynamic array challenge.
Right.
Where we can add or remove elements, making it all a bit more, unpredictable.
Yeah, having that dynamic data adds a whole other level of complexity. We have to make sure our strategies can adapt to that environment when it's constantly changing.
So how do we deal with those shifting sands? Like, let's say we already found a peak, maybe using binary search, and then we add a new element. Is everything we did useless?
Not necessarily. The key is to think about how, adding or removing an element affects what's right around our existing peak.
What's right around it?
Yeah, instead of rerunning the whole algorithm from the beginning, we can just focus on those elements next to the current peak and, of course, the new element we've added or removed.
I see. So if we add an element that's smaller than the current peak, and it doesn't really affect the peak's immediate neighbors, then we're good, right?
Exactly. We don't need to do anything unless the new element is bigger than the current peak, or if it changes the relationship between the peak and its neighbors.
Gotcha. Okay, so let's say we add an element that is larger than our current peak. What do we do then?
Then we have to see if this new element has knocked the old peak off its throne, right? If the new element is bigger than its neighbors, then it becomes the new peak.
And if it's not bigger?
If it's not bigger than both of its neighbors, then the old peak could still be the real peak. We'd have to do a quick check to be sure.
And how about removals? Are they handled the same way?
The idea is the same, but they can be a little trickier. If we remove an element that isn't the peak and doesn't, directly affect the peak's neighbors, then we're usually okay.
But if we remove one of the peak's neighbors, we need to take a closer look.
Exactly. We need to see if the peak can still hold that title after its neighbor goes away. If we remove the smaller neighbor, the peak is probably fine. But if we remove the larger neighbor, then we have to look at the other side to make sure the peak isn't smaller than that element.
So the key is to just analyze the local impact instead of redoing the whole calculation.
Yeah, that's what efficient dynamic peak finding is all about. Think of it like a chess game. Every move changes the board, but we only care about a few key spots.
I like that. This has been so cool getting into all these peaks and valleys, learning about the algorithms, and also like the strategies for adapting to all these changes.
And it shows us something really important about how to design algorithms.
What's that?
Sometimes the most elegant way isn't to brute force it, it's to understand the relationships within our data and use that to make smart updates in just the right places.
Well said. I think we've given our listeners plenty to think about today, from binary search to dynamic arrays and everything in between.
Yeah, and as always, we encourage you to experiment, explore and share your own adventures with peak finding on our AI.Code.Cast forum.
Until next time, keep coding, keep learning, and may all your algorithms reach new heights.